Good morning, or good afternoon, good evening, depending where in the world you are. My name is Khoshelham. I'm an assistant professor at the University of Melbourne. And today I have the pleasure to talk about Lidar high definition maps and autonomous driving. So I will start talking about autonomous driving and a requirement for autonomous driving, which is high definition maps. I will introduce Lidar, which is the main sensor for collecting data to generate high definition maps, and vehicle positioning, which is the purpose of high definition maps. I will then conclude with a summary and a discussion of open challenges. I think we all find autonomous vehicles a cool technology, but the actual benefit of autonomous driving is safety. Statistics from various organizations show that human error contributes to 94% of road accidents. Autonomous vehicles make fewer mistakes, and that results in safer roads. But it's also widely accepted that autonomous vehicles will lead to improved traffic flow and reduced carbon emissions. But maybe more importantly, autonomous vehicles will provide a mobility option for people with disability and special needs. Now, when we talk about autonomous driving, we need to define what it actually means. There are 5 levels of autonomous driving. Level 0 is basically manual driving, where the human is in charge of the vehicle. Level 1 is when the vehicle can do one task automatically. Level 2 is when the vehicle can do several tasks. And today, vehicles are capable of doing several tasks. For example, adaptive cruise control, when the vehicle can adjust the speed, maintain the speed, and brake when there's a vehicle in front of it. Also, lane keeping, for example. Level 3 is when the vehicle can drive the vehicle, basically self-driving, in known road conditions. So that means when we have a map of the road available. Level 4 and level 5 are the more advanced levels of automation, where basically the vehicle can drive, self-drive under all conditions, even without a map. And in level 5, basically only the vehicle is in charge of driving, and the human driver is not in charge. What we see in near future, the technology that we think in near future will be available is level 3 of self-driving, because that most of the developments today are for self-driving with a map. Now, when we talk about the map, what kind of map do we mean? So this is what we call a high definition map. This term was actually used for the first time by industry, a company called HearMap, which was involved in Mercedes-Benz Intelligent Drive project, which was the first project that demonstrated autonomous driving with a detailed 3D map in a long stretch of road in Germany, about 103 kilometers, back in 2013. So that was the first time that the term high definition maps or HD maps was used. But it basically means a very accurate and detailed 3D map of the road environment with all the traffic related objects included in it. Usually HD maps, they contain 3 layers. The first layer is a model of the road boundaries. There is usually a lane layer where you have the information about the lane boundaries, and then all the landmarks and traffic related objects, and also road markings. There are different representations for HD map, and there's no standard and widely accepted representation. In a raw form, a HD map can be just a point cloud, the raw data captured by the Lidar sensor. But there are also companies that are working on generating HD maps in the form of voxel maps or object-based representations, object-based models. For the generation of HD maps, the sensor that's commonly used is the Lidar, which captures 3D data by using laser light. So if you've looked at autonomous vehicles, the main players in the autonomous vehicles industry today, you see that all of these vehicles, they have a LiDAR sensor on top of the vehicle, maybe except Tesla, but all the other autonomous vehicle developers, they use LiDAR. And LiDAR basically serves as the eye of autonomous vehicles because it can capture the road environment around the vehicle in 3D with high accuracy and detail. Now, LiDAR can do several things. The primary purpose of LiDAR sensor is driving scene perception to understand the road environment around the vehicle and all the other objects, pedestrians, vehicles, and traffic-related objects. But the LiDAR on board the vehicle can also be used to capture data to generate HD maps. And that HD map with the LiDAR data can be used for vehicle positioning. Now, I said that there is no standard for in terms of the representation of HD maps. But there are a few formats that are commonly used. On the left, you see a labeled point cloud. That's basically the most basic representation for HD maps, which is a point cloud where points are labeled according to their type. So basically, by doing a semantic segmentation of the point cloud, we can generate these kind of HD maps more or less automatically. But the disadvantage is that it has limited semantic information. So usually the points only have the label, which represents the type of the objects. And point clouds take a lot of space. They're quite large in size. Voxel maps is, you see the figure in the middle that shows a voxel map, basically a 3D grid of voxels. Sometimes we call this a Minecraft model because in Minecraft game, a voxel representation is used. Generating voxel maps is easy. It can be automatic. It can be retrieved or accessed quickly because, for example, when you have a voxel map on a server and the vehicle wants to retrieve only the part that's related to its location, retrieving a local part of this HD map in the format of voxels is easier and quicker. Voxel maps are also suitable for crowdsourcing. So the idea is that all autonomous vehicles with the LiDAR sensor can contribute to data collection and mapping the road environments. And voxels provide a way to do it in a crowdsourcing form. But voxels also, they also take a lot of space and they're quite large. So handling, imagine you have a voxel map of a whole city with a high resolution. And obviously, it's a huge volume of data. The last representation is object-based representation or a landmark model, which is usually generated manually. And that manual process is slow and expensive. But then that's a model that contains a lot of semantic information. So usually you have, in addition to the type of objects, you have additional information you can include in the HD map. And it's quite lightweight and easily can be accessed and downloaded. Now, I mentioned that LiDAR is the main source of data for generating HD maps. But you might think that camera images are better because it's easier to identify objects in RGB images. And it's true, but LiDAR has advantages, especially it's independent of the ambient light in the environment, so it can work at night or in bad weather conditions. And in this video here, you see an example of detecting objects in RGB images and LiDAR data by fusing the two data sets. But the main advantage of LiDAR is during the night. So I will fast forward. So you see here, when the vehicle is driving at night, sometimes you see, for example, it picks up objects that you don't really see in the camera image. So this is picked up by the LiDAR sensor because it's independent of the light. All right, now when you create a HD map, the main purpose of HD map is for vehicle positioning. The primary technology for vehicle positioning is GNSS, Global Navigation Satellite System. The problem with GNSS is that it's not always available. So if you drive in a busy city center with a lot of tall buildings around you, usually you don't get GNSS signals. So urban canyons, tunnels, indoor parking lots, these are areas where we don't have GNSS. So we're looking for technology that can complement GNSS, and LiDAR is one of the best solutions. There are different ways to do vehicle positioning using the LiDAR sensor. One method is what we call a LiDAR odometry, basically by registering consecutive scans, you can estimate the local motion of the vehicle. And if you start from a known position, for example, the last position where you had the GNSS signal, then by estimating these local motions, you can estimate the position of the vehicle in a global coordinate system. The problem with LiDAR odometry is that you have small errors that accumulate in each registration step. And after some time, even though LiDAR data are quite accurate and the registration is quite accurate, after some time, your estimated trajectory would drift from the actual trajectory. The other solution is to register your LiDAR scans with an existing map, with a HD map, and that is advantageous because you don't have the drift problem. So basically, by registering your LiDAR scan with a reference map, which can be, again, a point cloud, a georeferenced LiDAR scan captured in the previous time, you estimate the position of the vehicle. The problem is that there might be differences between the two LiDAR data sets, between your rover scan and the reference scan, because these are captured at 2 different times, and the road environment might have changed between the two data collection times. So the registration might fail. And that's why there is usually a third solution, that you combine these two. You can do visual odometry by registering consecutive LiDAR scans. And from time to time, you also register your LiDAR scans to the HD map to correct for the drift. In addition to that, you can also combine your LiDAR positioning with GNSS when it is available. And the purpose of integrating LiDAR with GNSS is not really to increase the accuracy of the positioning, but to increase the availability, because GNSS is not always available. LiDAR registration might fail, for example, when there are changes in the environment between the time that the reference map was collected, the HD map, and the time you're driving. So then when you integrate these two solutions, your availability of the positioning solution would increase. So this graph here shows the availability of positioning solution when you use GPS and Baidu, and when you use LiDAR, and when you use an integrated LiDAR and GNSS solution. So you see the green bars, they show higher availability, which is the advantage of integrating LiDAR and GNSS. All right, there are still a few important challenges in the application of LiDAR for autonomous driving. I think that the main challenge is scene understanding from LiDAR data. We want to be able to automatically interpret the LiDAR data and understand its content. We want to be able to recognize objects in LiDAR data. The state-of-the-art approach to this is using supervised machine learning methods, using deep learning methods, for example. But supervised machine learning has a few problems. One is that it requires annotated data, labeled data. And when it comes to point clouds, annotated point cloud data is scarce. It's hard to annotate Lidar data. The other problem is that when you train a model, a machine learning model, usually it's scene dependent. So imagine that you train a network to identify objects using data from Melbourne, and then you want to use that on a vehicle that's driving in Paris or in a city in the United States, for example. The road environments are different, there are different types of objects, and your trained network may not perform well. So I think some of the solutions that we see today in research, being researched, one is the application of synthetic samples for training supervised machine learning models. And the other one is domain adaptation or scene adaptation, which can be done unsupervised with unlabeled data, basically. And also incremental learning of machine learning models. When you drive in a new environment with new objects that you didn't have, so your network, for example, hasn't seen this object before during the training. When you see it during the test, if your network can identify it as a new object and return it to the user for labeling, and then you can incrementally train your network to improve performance. So I would like to show you some of the result of our research that my students are doing. One is using synthetic samples for training machine learning models for identifying objects. We've developed an adversarial framework with a generator and a discriminator. And when you train these two modules together, then basically it can generate synthetic samples that can improve the classification performance on a point cloud. So here in the table, in the figure, you see example objects. So we train the network with real LiDAR samples, and then it generates synthetic samples like these ones that look pretty much like the real ones. And when you combine these synthetic samples with real samples to train, for example, a classification network or a segmentation network, then we observe a significant improvement in the performance of the network. Another line of research is scene adaptation or domain adaptation. And imagine that you have a network, for example, segmentation network trained on a source scene, and then you want to apply this to segment the target scene. You have buildings, for example, in both scenes, but they look different. You have, for example, tall buildings and short buildings. So the idea of scene adaptation is that the network will learn alignments between data in the two source and target scenes, but also features between the two scenes. And this can be done with unlabeled data in an unsupervised manner. So the experiments that we've done, and you can see here some of the results. By doing this data alignment and feature alignment, we see an improvement in the performance of the network using different backbone network segmentation networks. All right, to summarize, autonomous driving has a huge potential. It will lead to safer roads, and it provides a mobility option for disabled people and elderly people, people with special needs. And LiDAR is a key technology for autonomous driving. We talked about high-definition maps, which are a requirement for autonomous driving with the technology that we have today, we're developing today. It's all based on, it requires high-definition maps. But there is no standard representation for high definition maps. So we see raw point clouds being used as a high definition map or a voxel map or object-based models. And these are the three primary representations that are being developed. In terms of vehicle positioning, the LiDAR sensor together with a HD map can be used to estimate the position of the vehicle, but usually we integrate that positioning solution with GNSS to improve the availability of the positioning. So in the end, we want to have ubiquitous positioning that's available anywhere, anytime. There are a few research challenges that we discussed today, but I think in future we need to do more research on the use of synthetic samples for training supervised machine learning models to be able to understand point clouds and automatically interpret and identify objects in point clouds. Scene adaptation, domain adaptation methods, I think they are going to be very important for the future of autonomous driving, but also incremental learning and the ability to detect out of distribution objects that are new to the network when you drive in a new scene, and be able to train the network incrementally using just a few labeled samples. So single shot learning, few shot learning, I think will be very important in the future. I would like to acknowledge the contribution of students and colleagues to the work I presented today. And if I'm not available during the conference, if you have any questions, please feel free to send me an email. Thank you very much.